All right, we're back. We're on page 295. We're continuing our quest to be the best calculus students we can be. And let's see what we're going to learn this time. So there are two very common but very different looking notations for derivatives. And part of that, there's actually a third, which is attributable to Newton, which even though Newton was right there at the beginning creating all this stuff, his notation didn't really survive. Most of the notation that we actually use comes from Leibniz, who was they created it at the same time. You should definitely look up the history of calculus. It's incredibly interesting. A lot of controversies at the beginning. But anyway, we have what's called prime notation, and we've seen that, right? F prime of x being the main example, and 95% of prime notations are saying f prime of x equals something. You could also just have y prime. That's another possibility. That's from Lagrange. Lagrange is someone whose name you will definitely forget going forward. You'll remember it again when you get to Calc 2. And in Calc 2, when you talk about the error involved in a series, you're going to talk about the Lagrange error bound. And it's going to drive you nuts for 3 days until you really work out what's going on there. And then we have this other called the differential operator notation. So that's dy dx, df dx, d dependent variable over d independent variable. So this is from Leibniz. This is a good notation, but it gets out of hand later in life. But let's see what it looks like right now. So if I told you that what should I tell you? The something of something, let's do that a is a function of r is going to be pi r squared. I don't know why it took me so long to come up with any function of another variable, but it did. I settled on the area of a circle, right? The area is pi r squared. So if I want the derivative of this, I could say it's a prime of r is whatever it is, right? So I happen to know what it is, but it doesn't really matter. The notation is a prime of r. Another notation that you could use is you could say dA, right? Because a is the dependent variable. The area depends on the radius. So the rate of change of the area, so dA, dr, because r is the independent variable. That's the other. These are equivalent. They mean the same thing. I forgot the S. So those mean the same thing, which means you can use either. They both have places, right? You're going to fall in love with prime notation initially because it's just easier to use. The differential operator notation, first of all, that's what your calculator does, right? If you ask your calculator for a derivative on your calculator, if you do the derivative of natural log of x, it's going to look like this. That's your differential operator notation. And then we know that this is 1 over x when x is greater than 0 because we memorized that. So that also has its own uses. So you just got to keep in mind, the differential operator notation, a little trickier, but it's going to be with you longer, I guess, is what I really want to say. All right, write the derivative of y equals x to the negative second in a whole bunch of ways. So to refresh your memory, we found the derivative of that a while back. So we actually found it. This is going to be a very dark highlighter. We found it here, right? So we know that it's negative 2 over x cubed. So that's where I'm getting this from. I'm not doing something magical. All right, prime notation. So for prime notation, I'm just going to write that y prime is negative 2 over x cubed. That's fine. Differential operator notation. I kind of have two options here. So I could say y is the dependent variable, so dy. X is the independent variable, so dx is equal to negative 2 over x cubed. Or I could say that the derivative with respect to x, so d dx, the derivative with respect to x, meaning that x is the independent variable. That's what with respect to means. I feel like, I don't know what form of the English language they were using at the time when with respect to became the default thing. D dx, the derivative with respect to x of, now I give it the function, right? So think like your calculator. And this would be negative 2 over x cubed. So why are these notations equivalent? Well, from this note, the d dx notation, we definitely know that y is equal to that. So we're finding d dx of y. If you had to write that 1,000 times, which you basically do when you're inventing calculus, you very quickly decide, maybe I'll just put it here and live with it. And that's basically what we did. So we have the different notations. They're good for different things. df dx, again, going to come up a million times in a lot of applications that we can't even conceive of those applications yet. It's going to come up a ton. F prime is the nicest version because it's just functional, right? It's like literally functional. It's a function notation. So it's easy to say that you're going to sub in something. Here, if we have df dx, we have to use such that. And then you put the number at the bottom because eventually in life, you're going to have two numbers, one at the bottom, one at the top. But we don't know that yet, right? So we put it at the bottom. And then prime notation, if it's not functional, will also require that. So this sometimes, especially as you do more, will be written as this. So you can just turn y into y is a function of x, right? So we might as well just write y prime of x, but that's really uncommon. Like in algebra 1, you never write, like if you have y equals 3x plus 2, you could easily write y of x. Name the function y of x is equal to 3x plus 2. You just don't do it. I don't really know why. All right, time trial. Get these done first. Well, I know that I'm going to win because I'm the only one doing it. Also, my sock's falling off. Got it. All right, find the derivative using the limit definition of the derivative as a function. All right, so should we do this? Roll up the sleeves. Here we go. Y prime. That's not even right. Here we go. Y prime. The limit as h approaches 0 of f of x plus h minus f of x over h is going to be the limit as h approaches 0 of h over h, which is 1. Okay, that's fine. Limit, so this will be y prime, as h approaches 0 of x plus h squared minus x squared over h, which is the limit. So you're just kind of racing here. 2xh plus h is really good practice for expanding binomials. I don't know why you need to practice that, but this will become the limit as h approaches 0 of 2xh plus h squared. I should have reduced out the h there. Could have picked up some time. Limit h approaches 0, 2x plus h, which is just 2x. I'm going to say 2x to the first. Why not? I'm going to stop writing the like x plus h to the whatever, and I'm just going to start expanding them. Y prime is, so it's going to be the limit. Oh my God, almost forgot that. Limit as h approaches 0 of x cubed plus 3x squared h plus 3x h squared plus 1. Nope, plus h cubed. What the heck? Plus h cubed minus x cubed all over h, which is the limit as h approaches 0 of, we're going to cancel, 3x squared plus 3xh plus h squared, which is 3x squared. Okay, so the derivative of x squared was 2 times x to the first. The derivative of x cubed was 3 times x squared. Is there a pattern? Maybe. Let's do a couple more. Y prime, or dy dx if you prefer. It's a little slower. The limit as h approaches 0 of, all right, so it's 14641. So it's going to be x to the fourth plus 4x cubed h, whoa, plus 6 x squared h squared plus 4 x h cubed plus h to the fourth, and then minus x to the fourth over h. All right, we're going to cancel and cancel. Cancel in the numerator, anything without an h, cancel an h from everything in the numerator that's left over. H approaches 0 of, it's going to be 4x cubed plus 6x squared h plus 4x h squared plus h cubed. Is anybody else getting tired of this? I know in class, people usually get very tired by now, but I keep going. But I bet that most of you are not going to keep going here. 4x cubed. The derivative of of x to the fourth was 4x to the third. So it looks like the exponent becomes a coefficient, and then you subtract 1 from the exponent. So I'm thinking that here, dy dx, or y prime, should end up, I'm going to bring the exponent down and then subtract 1 from the exponent. And if you check on your calculator, you will see that that is correct. Here, y prime will be bring the 6 down and subtract 1 from the exponent. And if you check on your calculator, you will see that that is correct. All right, so what I'm going to do is I'm going to end here. I don't know. See if you can work out what's going on there. We'll be back in the next video to state exactly what's going on there. But we are making progress. This is a kind of a big moment for us. We're working out how to find the derivatives of what are called power functions, right? Which is a variable to a constant exponent, which someone should have told you a long time ago, but probably no one ever told you that that's called a power function. So I will be back in the next video and we will talk about that. So I will see you then.